Okay, so, and maybe anyway, let's start. So it's my pleasure to introduce today's speaker, Eric Marberg from Hong Kong, and he will talk about Gelfand W-graphs and perfect models. So please go ahead.
Okay, so thanks everybody. Thanks for the opportunity to speak in this seminar. So this talk, any new results are joint work with my student Yifeng Zhang. And just to start out, a few conventions throughout the talk. So just for simplicity, I'm going to define all representations and all vector space and everything just over the complex numbers. Though I think basically most statements will still be true over the rationals or the reals or something like that. But just for simplicity, we'll just stick with C. And then for any finite group, I just want to let IRR of G be some fixed set of irreducible G representations, just with one representation from each isomorphism class, and then make the same definition if we're working with some kind of algebra or anything like that. And then, with this setup, a Gelfand model, I'm going to use this term, for G is just a G representation that's isomorphic to this direct sum over all irreducibles like this. So it's convenient to have this terminology. Gelfand model is just some representation that contains every irreducible representation with multiplicity 1 up to isomorphism. And then throughout the talk, let n be a positive integer. And some groups that we'll see, well, we have, for example, the symmetrical will show up a few times. So this is just n by n permutation matrices. Or we'll think of this as permutations of 1 up to n. And then also I want to have some notation to refer to these other classical Weil groups. So WNB will just be the n by n sign permutation matrices. And this will contain WDN, which is the n by n even signed permutation matrices. So here, sign permutation matrix is just a permutation matrix, but you can change some of the 1s to -1s, and even sign will just mean there's an even number of -1 signs. All right, so here's the first problem I want to talk about. And most of this first part of the talk will be mostly expository and some preliminaries to set up results in the second half. So I want to talk about the notion of an involution model and why this is a natural thing to think about for certain finite groups. So in this setup, let G be a finite group. And then we have this well-known fact that if G has all real representations, where real, I mean like realizable over the real numbers, then we can say that the sum of the degrees of the distinct irreducible representations of G is equal to the number of involutions in your group. So the number of elements G that are equal to their inverse in G. Okay, so and let's call this set I of G. So suppose we want to construct some Gelfand model for this kind of group. Meaning a group G where that has all real representations that satisfies this identity that I just wrote down. Then a natural place to look for a Gelfand model is the subspace C I of G, meaning the span of these involutions inside the usual group algebra of G. Since this subspace at least has the right dimension. There's even a natural G action on this space. By conjugation. So a given element, H will just map G to H, G H inverse. Okay, so we're looking for a certain representation that has whose degree is the number of involutions in our group. So here's a vector space that has that dimension, and it even already has a G action. So problematically, though, this permutation representation is usually not multiplicity free. Okay, so we can ask then, well, what is the simplest way of generalizing or extending this representation on involutions like this? Well, we can just try to add some coefficients. So rather than working with a permutation representation, where every element of G is acting as some permutation matrix, we can look for a monomial representation. So a representation where every element of G is acting as a permutation matrix where we change some of the ones to arbitrary non-zero scalars. So to be more specific, what we can look for is we can try to find a map lambda that goes from G cross involutions in G to C, such that what we want to have happen is we want this formula H sends G to lambda H of G, HG, H inverse to be a G representation. And we want this representation to be a Gelfand model. And when we can do this, we say that G has an involution model. I guess just a remark here. So finding such a map lambda is equivalent to choosing one-dimensional representations of the centralizers of each conjugacy class inside the set of involutions, such that we get a Gelfand model when we induce all of them to G. And then add them together. Okay, so an involution model is equivalent to this construction, and it's just kind of the simplest representation you could make in this natural subspace that has the dimension equal to the sum of the dimensions of all your irreducible representations in the event when those are all realizable. So an example of this kind of construction is we can look at the symmetric group. The symmetric group Sn has all real representations. In fact, all of them can be defined over the rationals. The involutions in Sn are the permutations whose cycles all have length 1 or 2. So they are fairly tangible objects. So something like 1, 2, 3, 5, 3, 6, 5, 4, 8, or something like this. 7. In cycle notation. So here's how we can define this map lambda to get an involution model for Sn. What we will do is define lambda of W comma, let me say HG, to use my notation from earlier. I'm going to define this scalar to be -1 to the number of inversions so these are pairs ij of H that are cycles of G. So where inversion, I mean I is less than J and H of I is greater than H of J, like this. So we have this relatively simple formula. And then there's this theorem, which I'll attribute, I guess, to Aidan Roykman and Postnikov, though it might have kind of existed earlier in the literature or in different forms. Well, the resulting, the formula H sends G to lambda HG times HG H inverse defines representation, let's say a Gelfand model of Sn on this space C-span of involutions in Sn. So we have this pretty simple formula. Okay, so in fact, well, recall, that we can, let me say, so recall that a Coxeter group is a group W with a set of generators S, which are all involutions inside W, such that we can write W is isomorphic to the finitely presented group S generated by S and S, subject to just some relations ST to certain numbers MST equals 1 for some function from S cross S to Z. Okay, so this being a little bit vague, but this I think is more or less equivalent to a definition of a Coxeter group. So the classification of finite Coxeter groups is well known, and all finite Coxeter groups including Sn, these groups of sign permutation matrices, the dihedral groups, have real representations, have all real representations, but they don't all have involution models. In fact, there is an explicit classification due to mostly to Baddeley from the 90s, and then extended from Weil groups to Coxeter groups by Van Root in the 2000s, that says that a finite Coxeter group has an involution model if and only if it has no irreducible factors of type D2n, E6, E7, E8, F4, or H4. So the big things that are excluded here are the type D and even rank, but the other classical groups have involution models. Okay, so a theme of this talk and the results that I have to tell you about is sort of what is the right notion, the right generalization of an involution model for the Iwahori-Hecke algebra of a Coxeter system. So let me briefly recall the relevant definitions. So let WS be a Coxeter system. So a Coxeter group with a set of simple generators, and write L for the usual length map, which tells us the minimum number of factors from S we need to multiply together to give any particular elements of W. And then also let Q be an indeterminate. Then there is a unique algebra, which I'll write as H, that depends on W and S. And I'm going to define this over this ring of Laurent polynomials in Q, and we'll just use complex numbers. The rational numbers will also serve just as well. So there's a unique algebra that has a basis indexed by elements of W. And with multiplication satisfying, well, if you take HW and you multiply it by HS, then you either get H times WS or I guess, may I write it this way? It doesn't, both ways are fine. If I take HS and I multiply by HW, I either get HSW or I get HSW plus Q minus Q inverse HW. And in the first case is when the length of L of SW is greater than the length of W, and the second case is the reverse. And here, this is for S in S and W in W. So this multiplication doesn't tell us how to compute any product. It's just telling us how to compute products of simple generators and arbitrary elements, but this is enough to compute these formulas for any product if we want to by iterating this formula. So I'll just point out that the units in H is just this element, which is H1, the basis element indexed by 1. And just to motivate very briefly, so we want to study the representations of H in order to better understand the representations of Lie groups with vowel group W, or modular representations of W, etc. So very vaguely, so this is an interesting algebra to study for those kinds of applications. So we have this algebra, and then I want to talk about a way of constructing representations of this algebra H. So very simply, so I'll just give you the definition first, and then I'll try to motivate it, since the definition at first glance seems a little bit technical. So we start out with some set V. So V is a set with maps tau that go from V to subsets of simple generators of our group W. And then also a map omega that goes from V cross V to our scalar ring. And then the data gamma is vertices, we have tau and we have omega, is a W graph if there is an H module structure on the sets of formal linear combinations of elements of V. So I'll just say some basis YV that's indexed by V, satisfying the following formula. What we want to have true is we want to have I'll write it like this. So we want to have HS plus Q inverse times YV. And we want to be able to express this by a formula that depends only on these maps tau and omega in the following sense. So either this formula is going to give us Q plus Q inverse times YV, or it's going to give us the sum over all U in V, where S is not an element of tau of U, and we have this coefficient omega UV and then YU. And the first case is if S is not in tau of V, and the second case is if S is in tau of V. And here, S is in S and V is in V. Okay, so this is a kind of oddly specific formula for a module structure, but this turns out to be fairly flexible. So we call this data a W-graph because we can just view gamma as a directed graph on V with edges that, U goes to omega of U comma V when this number omega UV is non-zero. So just drawing that labeled directed graph almost encodes everything you need to know about gamma. We also need to know the values of tau at each vertex, which would not be included in this directed graph, but most of the important features are just determined by this graph structure. So this is our definition of a W-graph. Now let me give you the motivating example that makes this a natural thing to consider. So there is a unique ring involution on this Hecke algebra H. And I'm going to denote this as just an element H goes to H bar, satisfying two properties. So one, it changes the scalar Q into Q inverse, and it changes the generator S into HS inverse, which is just HS plus Q inverse minus Q for S and S. Okay, so showing this, that there exists this ring involution is relatively elementary. But then there's a much more powerful theorem due to Kasdan and Lustig, (1970s), that says two things. So it says that H has a unique basis, which I'll denote by CW, satisfying CW is equal to CW bar. And it also holds that CW can be written as HW plus the sum over all Y in W with the length of Y less than the length of W of HYW HY for some polynomials HYW. And the key thing about these polynomials is that they have no constant term and they only involve negative powers of Q. So this theorem looks a little bit abstract, saying that there exists this basis, but I'll just say that the uniqueness of this basis essentially boils down to this bar invariance under this unique ring evolution, and the fact that there are no polynomials in Q inverse with no constant term that are fixed by this bar involution. And then the existence is secretly kind of just given for free. So the conditions that govern this basis tell you an inductive way of constructing it if you want. Okay, but there's more to this theorem, which is the following. So moreover, if we define tau of W to be the set of generators S in S that increase the length of W, and then we set omega of YW to be either 0 if tau of Y is contained in tau of W, or the coefficients of Q inverse in this sum HYW plus HWY in the otherwise. Then this triple gamma tau omega is a W graph, which we'll call the left Kasdan-Lustig W graph. So this is our motivation for this definition of a W graph. It sort of abstracts the action of H on this special basis CW, the Kasdan-Lustig basis. So let me give you a quick example. So the left KL W graph for W equals S3 is just this picture 3, 2, 1, 2, 3, 1, 1, 3, 2, 1, 2, 3, 2, 1, 3, 3, 1, 2. There's an arrow going here and here, and then arrows going here, and then arrows going up and down. And in this example, all of the edge labels are just 1. Okay, and I'll just point out that the W graphs are fairly flexible construction, since actually can be shown that if W is finite, at least if W is finite and crystallographic, then every irreducible H representation arises from a W graph. Okay, so for any finite or any Cox group whatsoever, we have a Kasdan-Lustig W graph. But that is kind of a big representation. So a natural thing to ask is, how would we decompose it into smaller pieces? So this is where we introduce the notion of cells. So the strongly connected components in a W graph are its cells. And each of these inherits a W graph structure. Moreover, strongly connected means that for any two elements in a cell, there's a directed path from one element to the other, and also a directed path from the second element back to the first. Now, if you have your W graph and then you circle the strongly connected components, then the cells themselves form a directed acyclic graph. So the key thing is acyclic, because if there were any cycles, then that would mean that two of your cells are actually strongly connected, but they're not. And then this directed acyclic graph will induce or define a filtration on the H module of your starting W graph whose successive quotients are the H modules of the cells. So this is how finding the cells in the W graph are going to give you a decomposition of your original H module. Though the cells are not literally submodules, but they define this filtration. And then in general, when we talk about the left cells in W, these are just the cells in the left Kasdan-Lustig W graph. So if we turn back to our SN example, so the cells here are going to be these elements here, and then these elements here, and then we have two cells that are just of size 1, like this. And then you'll notice the directed acyclic graph that's relevant here is we have some picture like this. Okay, so one more thing to say is, well, most edges in the left Kasdan-Lustig W graph have the form y goes to W, where the length of y is greater than the length of W. And in general, it's actually true that if y to W is an edge with the opposite length convention, where the length of y is less than the length of W, then it must hold that W is equal to S times Y for some S in S, and there must be an edge in the reverse direction like this. So most edges have a certain direction of the length changing, but not all edges. But whenever you do see an edge that is going to increase the length, there's always going to be an opposite edge that complements it. So we call these this situation where we have two edges like this, bidirected edges in a W graph. And the sets of vertices, or let's say the components in a W graph that are connected only by bidirected edges are called the molecules. So say molecules don't inherit a W-graph structure, unlike cells, but they're often easier to classify. Okay, and in the symmetric group, something especially nice happens. And we can already see this in the small example that I did. So this result also dates back to Kasdan and Lustig's original paper. Well, it turns out that every or let me just say, before stating the full theorem. So generally, any cell in a W-graph is a union, a disjoint union of one or more molecules. So the molecules are giving you a finer decomposition than the cells. But in some situations like SNs, we have this nice thing that occurs. So every molecule in the left Kasdan-Lustig SN graph is a cell. So cells and molecules in the Kasdan-Lustig graph of the symmetric group are the same. Moreover, the cell representations of HFSN are all the left cell representations of the Hecke algebra of the symmetric group are all irreducible. Finally, one can classify explicitly the left cells in terms of the combinatorial RSK correspondence which is a bijection that takes a permutation and gives us a pair of standard tableaux of the same shape. So this is in Sn, and this is a pair of standard tableau of the same shape. And the way this explicitly works out is two elements V, W, and Sn are in the same left cell if and only if they're recording tableaux. So the second tableau assigned by this RSK correspondence is the same for both entries. So I don't have time to, I'll skip kind of the fairly well-known explicit description of the RSK correspondence, but I just want to comment that there is also a right-hand version of all this. Where the right KLW graph is defined by exactly the same construction except we define tau of W as the set of right ascents instead of left ascents. But everything else is the same. And in general, the right cells, or the cells of W, which are defined to be the cells of the right KL W-graph, are always just the inverses of the left cells. So meaning they're just sets of the form C inverse like this. Okay, so this is kind of the first half of the talk, and so the main takeaways in involution models for finite Coxeter groups give us a canonical construction of irreducible representations. Because if you have an involution model, then every irreducible occurs as a unique subspace, subrepresentation. On the other hand, at least for nice Coxeter groups like the symmetric group, we can use W-graphs to get a non-canonical construction of, again, all the irreducible representations of the Iwahori-Hecke algebra. What's non-canonical here is that many cell representations will turn out to be isomorphic. So in part 2 of the talk, I want to discuss how we can extend and combine these approaches and generalize them. So this is kind of a good midway point.
Go ahead whenever you are ready.
Okay, great. So we continue with part 2. So the question after introducing these constructions, involution models, and W-graphs for the second part of the talk is, well, what is the right, or what's an interesting analog of an involution model for the Iwahori-Hecke algebra H? So just to start out with some observations, for our ring of scalars, Laurent polynomials over C, but even if this was just Laurent polynomial over the rationals, the C is not really important here. The algebra H that we introduced a few slides ago is split semi-simple, and there's a bijection, a dimension or a degree preserving bijection between irreducible representations of H and irreducible representations of W. So the subspace that's just the span of HW, where W is an involution in W, and this is inside H, still has the same dimension. Or let's say same degree as this direct sum over all irreducible representations. So we could try to kind of look for a Gelfand model in this subspace. So the problem, though, there is no longer a natural version of the conjugation representation. So things, nevertheless, there is almost such an action when W is the symmetric group in the following sense. So here's what we're going to do. So we need to restrict to a smaller subspace. So define IN FPF to be the set of fixed point free involutions in Sn. So this is an empty set unless n is even. So we need to assume that n is even here. However, when n is even and you define the set, it does turn out, this is a result due to Rains and Vazirani, or a corollary. If we choose some parameter, u, it can be either q or it can be minus q inverse. Then there is a unique H of Sn module structure on the space spanned by fixed point free involutions. And I'll write the basis elements as just a MZ. Such that we have the following formula. If you have a generator in H and you apply it to a basis element in this space, it's going to give you what looks like Hecke algebra degeneration of conjugation. So we're either going to get H MSZS, or we're going to get MSZS plus Q minus Q inverse MZ, or we're going to get U times MZ. And here the conditions are something like if Z of I is less than Z of I plus 1, or if I plus 1 is not equal to Z of I, which is greater than Z of I plus 1, or else where we're assuming that S is equal to I plus 1, yes, in Sn, and Z is in INFPF. Okay, so this is almost like a permutation, a conjugation representation of the Iwahori-Hecke algebra on this space of involutions. But it's not quite large enough to have the right dimension as a Gelfand model. Nevertheless, there is a generalization of this construction for other types. So what we do is we have this following definition. We say that in elements Z in W is a perfect involution if Z is equal to Z inverse, so it's an involution in the usual sense, and for every reflection T in the set of conjugates of simple reflections, it holds that T and ZTZ commutes. So this is just kind of a technical definition, but this is the simplest way to phrase it. So for any reflection T and ZTZ commute, this is equivalent to just saying that T times Z to the 4th power is equal to 1. if you want to write it like this. Now, a quick example. So if W is Sn, then T must have the form Tij, which is just this cycle Ij for some I less than j. And so, and then we have ZTZ is going to be equal to Z of I, Z of j. And it will always hold that T and ZTZ commutes if and only if Z is 1 or Z is a fixed point free involution. Since the only way that T and ZTZ are going to commute, when we need Ij to be disjoint from Z of I, Z of j for all pairs Ij. So this will end up forcing Z to be fixed point free if we want this condition to be satisfied, and Z is not the identity element. So the conditions defining a perfect involution are preserved by conjugation. So perfect involutions in W are a union of conjugacy classes. And then we have the following results of Raines and Vazirani generalizing the type A phenomenon that I just described above, which is that if we choose, or let's say for each choice of parameter and for each perfect conjugacy class, K in W, I'll just say there is an analogous H module structure on this set, this space spanned by K. And so this H module gives a kind of deformation of a permutation representation or of the permutation representation tensored with a sign representation. Okay, so this almost gives us some ingredients to try to attempt a Hecke algebra version of an involution model construction. The problem we run into, though, is that conjugacy classes of perfect involutions are fairly rare. So in Sn, we only have the identity elements and fixed point free involutions. In W, in the vowel groups of type B and D, Z is perfect if and only if its image in Sn is perfect under the natural map that just erases the signs in a sign permutation matrix. So in our kind of natural surjection from the group of sign permutation matrices to ordinary permutation matrices. Okay, so this construction is a little bit too limited to find all irreducible H representations by the theorem above. But so what we can do is to solve this problem, what we'll do is we will combine representations from perfect involutions with representations from parabolic subgroups. So the construction that we introduce is the following. Given a set of generators, J, inside our simple generating set, let W subscript J be the parabolic subgroup generated by these elements, and then let W superscript J be the set of distinguished coset representatives, the elements W in W, such that the length of W times S is greater than the length of W for all S in J. In addition, I'll just say choose a set J, then choose a perfect, or a WJ conjugacy class of perfect involutions in WJ, and then finally let's sigma be any homomorphism. I will call this triple J, K, sigma a model triple. And there is a natural
sorry, what is K?
Oh, yes, I didn't write that down. The choose. So this is, skip some words. So the let K be a WJ conjugacy class of perfect involutions in WJ. So yeah, so we instead of choosing a perfect conjugacy class in W, we first choose a parabolic subgroup and find a conjugacy class there. And then we choose any homomorphism. So there is a natural action, W action, on the set that's just the direct product WJ cross K. And the action is, if you take a simple generator and you act on WZ, this gives you either SWZ if SW is in WJ, or it gives you WTZT if T, which is equal, which we define to be W inverse SW, is in J. Okay, and so it's a basic exercise about distinguished coset representatives, is that these two cases are mutually exclusive. We have, this is for S in S, as usual. We also define a length map by setting the length of this pair WZ to be just the length of W plus half the length of Z, but we take the floor in case the length of Z is odd. Okay, so in this setup, then we have the following proposition, I guess, is this is not too hard to derive from the results that have already been stated. Well, given a model triple, J, K, sigma, there is a unique H module structure on this this space M, J, K, sigma, which I'm going to define as just the span of these elements, formal elements, such that if S is in S and WZ is in WJ cross K, then we have this formula HS times M WZ. We have something like 4 cases. So we have either M dot WZ, or we have M S dot WZ plus Q minus Q inverse MZ, or we have minus Q inverse, or I should write M WZ. WZ, or we have just Q MWZ. And the relevant cases here are, first we have if the length of this product is increased, or if the length decreases, or if it happens that S fixes this element and sigma of W inverse S W is equal to -1. And then finally, if S fixes this element and sigma of W inverse SW is equal to +1. So we have this, this formula like this. And then the definition that accompanies this is, we'll say that a perfect model for W is a set of model triples P such that if you take the direct sum of these modules we've just constructed, this is isomorphic to the sum of all the irreducible representations. So it's a Gelfand model. Okay, so these ingredients of picking a parabolic subgroup and then picking a perfect involution gives us a flexible enough way of making Hecke algebra representations that are analogs of inducing one-dimensional representations of centralizers of involutions, that we can construct something something interesting. Okay, so this brings us to first domain theorem. So now we have motivated this construction. The first theorem to state is the following sort of surprising fact, which is that a finite Coxeter group has a perfect model if and only if it has an involution model. So that means, well, all irreducible factors must be of type an, bn, d2n plus 1, h3, or I2n. Or equivalently, no irreducible factors of type d2n, en, f4, or h4. Okay, so this is a kind of a good reason to think of a perfect model as the sort of a Hecke algebra version of an involution model, but this is maybe slightly misleading. So actually our proof of this is just coincidental. Following an explicit classification. So we don't actually know of any formal way to associate an involution model to a perfect model or vice versa. In certain types, the relevant constructions are fairly similar, but it seems like there's not actually a relationship between the two. So there's more to the story as well. So each perfect model also gives rise to a W-graph. So each perfect model may be turned into a W-graph. And the way this construction is as follows. So we'll need to state a theorem. So a perfect model P, or more generally, just any set of model triples, determines a representation, or determines an H module, which I'll call M subscript P, with a basis of the form mg for G in IP, where this is just the disjoint union over all JK sigma in P of these Cartesian products of distinguished coset representatives and consciously classes of perfect involutions. So there's some discrete explicit a set that indexes this basis. And then the theorem we need to turn things into W-graphs is the following. So assume P is a perfect model. So I guess I should say this theorem will mostly make sense if P is just any subset of model triples. But here are some properties that hold. So there is a unique Z linear map which I'll denote by M goes to M bar, such that we have HM is equal to H bar times M bar for all H and H and M in this module, and also with mg equal to mg bar equal to mg if G in this indexing set has length S dot G greater than or equal to the length of G for all S and S. So if in some natural appropriate sense, the index G is minimal with respect to the action of W. So there's this unique analog of the bar operator for the Hecke algebra. And then there is an analog of the Kazan-Lustig basis. So there is a unique basis that I'll write as CG for this module, such that with respect to this operator in the previous part, we have both CG is bar is equal to CG for all G, and we have CG equal to mg plus the sum over all H in our indexing set with length less than the length of G, some polynomials mhg times mh, where mhg is a polynomial in Q inverse with no constant term. So we have this, this analog of a canonical basis. And I'll just comment, well, it's a famous fact and recent fact, sort of that, that every HYW is actually in Q inverse times n of Q inverse. So there's positive coefficients, but this does not hold for mHg, so that we can see negative coefficients for some of these polynomials. And then there is a third part to this theorem, which says that we can make the following W-graph construction. So for G in our index set, define tau of G to be the set of S in S such that either L of S dot G is greater than L of G, or HS times MG is equal to Q times MG. And then further, let omega of H comma G to be either 0 if tau of H is contained in tau of G, or else the coefficient of Q inverse in this sum MHG plus MGH otherwise. And then the conclusion is that this set of indices with this tau map and this omega map is a W-graph. So the punchline here is that in this way, a perfect model for W gives rise to a what I'll call a Gelfand W-graph. So a W-graph whose associated H representation is a Gelfand model. Okay, so all of this becomes much more explicit if we focus on a particular group, and we don't want to write things down in such a general way. So I'll describe to you the way these constructions work for the symmetric group. So define Gn, capital Gn, to be the set of fixed point free involutions in S2n with the property that no I greater than n has z of I plus 1 less than the minimum of I or Z of I. Okay, so this is just kind of a clever way of referring to the following elements of S2n. So elements of Gn look like, well, first you have some permutation of n here. So you have a bunch of 2 cycles, just an ordinary involution like this. Maybe you have some fixed points left over. And then you have n plus 1, n plus 2, n plus 3, up to 2n. So this part here is just like an involution in Sn, but then you attach these fixed points that are left over in order to the numbers that are left over above n, like this. And then if there are any numbers left over in this part, they just are adjacent cycles like this. So there's kind of an obvious bijection between the set Gn and just the set of involutions in Sn, except we turned everything into a fixed point free element by adding cycles in a particular way. Now, I want to define a bunch of, or some descent sets. So for Z in Gn, I will let, or maybe I'll say, I can try to draw this all in one slide. I guess so theorem we can state is, so choose a parameter u, either to be q or minus q inverse. When I should attribute this. So this turns out to recover another result of Aden-Roykman and Postnikov. So choose a parameter u, and then there is a Gelfand model for H of Sn on the space spanned by mz for z in Gn, such that we have the following multiplication formula. So Hs times mz, there will be 4 different cases. So we either get mszs or we get mszs plus q minus q inverse times mz, or we get minus u inverse mz, or we get u mz. And at the end of this, this is going to be for s equal to this particular simple transposition, I plus 1. And the cases are, so we have this final case is if z of I is equal to I plus 1. And this penultimate case is if z of I plus 1 is equal to j plus 1 for some j greater than n. And then these 2 cases are if just z of I is less than z of I plus 1 and not in cases 3 or 4. And this is if z of I is greater than z of I plus 1 and not in cases 3 or 4. So the point is that if we take a little bit of trouble, we can write down a very explicit version of this kind of Gelfand model. So some relevant comments. Well, oops. So these two Gelfand models one for each choice of u, a parameter u, may be identified with the Gelfand model constructions associated to two perfect models. For Sn, so there's a way a natural way of turning the set Gn into a W graph, into an Sn graph. In fact, there's two different ways of doing this. Now, so also I'll say, well, there are similar explicit Gelfand model constructions for H of W when W is equal to a group of sign permutations or even sign permutations of odd rank. Also I'll say, well, we conjecture that or let me, before saying conjecture, so we can explicitly describe the molecules in the Gelfand Sn graphs that we just described above, and we conjecture that actually, or I should say, so we can describe the molecules in terms of a variance of the RSK correspondence. So there's an explicit characterization, and then we can conjecture that in every Gelfand Sn graph derived from a perfect model, all molecules are cells and all cell representations are irreducible. So we checked this up to about n equals 10 or something like that. Now I'll point out that maybe there's a natural question here, which is I just gave you a specific, one particular Gelfand model that we can be derived from a perfect model. Now in general, there's not a unique way of constructing perfect models for any of these Coxeter groups. Nevertheless, there are some uniqueness results that are relevant here. And the maybe I'll just present a very vague kind of summary theorem, which says that up to a technical but natural form of equivalence, any irreducible finite Coxeter group has at most has either 0 or exactly 2 perfect models, except in types A3, B3, and H3. So in the rank 3 types. So there's 2 caveats I should write here. So equivalent here morally means that the associated W-graphs are essentially isomorphic. And also, I guess there's a slight caveat for type Bn. So in type Bn, there's actually 4 equivalence classes of perfect models, but 2 of them are kind of trivial refinements of the others and can be excluded by adopting a slightly different definition. Okay, so that's where I'll conclude. So thanks so much.
Okay, and let's thank the speaker. So are there any questions or comments?
Yeah, I have some questions. So first, to this theorem, so what is the number in types A3, B3, and H3?
There's something like, they're like 8, 6, and 4 or something. There's just a bunch of, okay, so in A3, I can tell you exactly what happens. The issue with A3 is also D3. So there's a family of models for type A, for all AN, and there's a family of models for all D, type D odd rank. And when N is 3, they both contribute, so an extra family of models. So there's 4 instead of 2 because the A and D are overlapping. And then H3, I think, is just kind of an exceptional case. And then H3 and B3 are just kind of exceptional.
Because, I mean, my very naive thing, if you have in Coxeter group some classification with 3 exceptions, maybe there is some ADE type classification behind this, where these exceptions correspond to E6, E7, and D8 or something like that.
I don't know, but certainly, like, well, type E is kind of excluded here. So there's kind of no.
I mean that there is some object behind this which has ADE type classification where E reappears in those types A3, B3, and H3.
Yeah, there could be. Yeah, I would say. So there's definitely something. There could be something like that going on. I don't know what the answer is, but a lot of these perfect conjugacy classes they're often a shadow of something for some classical groups. So there's something going on
Okay, thank you. I have one more question. So when you defined the mu function for the representation, you first said that the analogs of Kazhdan-Lusztig polynomials for the representation might have negative coefficients.
Yeah.
And then you defined the mu function on the next slide can it also have negative coefficient? So this coefficient of Q inverse in blah blah blah.
Yes, yes. So yeah, yeah, it can be negative. So but it's there's sparse. It's kind of sparse examples. So one thing that happens, for example, is in the nice type A case where we have an explicit conjecture about the cells. Well, we can't actually find any negative coefficients for these values of omega. But if we consider the arbitrary A, B, D types, then we can compute enough examples where we will see negative coefficients.
Thank you.
Are there any other questions or comments? Okay, so it seems not to be the case. So let's thank Eric again.
Thank you.